Lab 4, spring motion. This lab analyzes the multidirectional motion of a spring using Newton's second law and the energy principle. The motion of the spring was analyzed in Tracker, and a model was made in Vital. The results show that the model followed the observed motion closely with little variation, and that the energy principle was fulfilled with delta E equaling 0. Newton's second law states that the net force on a system equals the mass times the acceleration. Manipulating this equation, we get that the final velocity equals the initial velocity plus the net force divided by the mass of the system times the change in time, and that our final position equals the initial position plus the average velocity over a time interval times that time interval. The equation for gravity force was also used. On Earth, Fg equals the mass of the system times the gravitational constant, 9.8 meters per second per second. The equation for spring force was also used. The spring force equals a spring constant specific for that spring times the change in length of the spring relative to L0, or the relaxed length. The equation for a period of a spring was also used, which is that T equals 2 pi, the square root of the mass of the system divided by K. Here's our Tracker video. Our initialization for our model, for an initialization, the length was found to be 0.7 meters, the mass was found to be 0.402 kilograms, our initial position was x equals negative 0.12 meters and y equals negative 0.641 meters. Our initial velocity was 0. Using this and the equations shown on the previous page, we found that the average time or period was 1.52 seconds, and we used that to find our K, which was 6.869 newtons per meter. And then, since our initial position, the velocity was 0, that meant that we had no change in F net, we knew that F of G equals F of S. So, using this equation, we were able to find our L naught, which was 0.126 meters. The energy principle states delta E equals delta W plus Q, or the work on the system plus the heat lost. However, because our system never moves from its position but only within itself, we know that our delta E is equal to 0. And our delta E is made up of the change in kinetic energy, the change in potential energy due to gravity, and the change in potential energy due to the spring, each of which is equal to its own specific equation. The kinetic energy is equal to 1/2 the mass of the system times the velocity squared. The potential energy due to gravity is equal to the mass of the system times the gravitational constant for Earth times the height of the system. And the potential energy of the spring is equal to 1/2 K L minus L naught. All of the equations were entered into the Vital code, which gave us this model here. This model shows a graph, as well as the motion, of all of the energies of the system. The potential energy for gravity is shown in green, the potential energy for the spring force is shown in red, the change in kinetic energy is shown in blue, and the total energy of the change in energy of the system is shown in yellow. Seeing as delta E is always at 0, we know that delta E for the system is 0, which follows exactly what we expected to see. Next, we ran a model comparing what we saw in Tracker to what we created in Vital, and the graph was displayed. As you can see here, the graphs are almost identical. There is some slight variation, but this can be attributed to drag or possibly to drag. All in all, as it should, the total change in energy of the system was 0, and the model and the actual data match up well, as shown by the graph in the previous slide. Thank you for watching.